César Muñoz. I'm the technical lead of the Formal Methods Group at NASA Langley Research Center.
My name is Hoogendijk. I work for Verum Software Tools.
My name is Colin Havelund, and I'm Technical Director at a company called D-RisQ here in the town of Malvern in the United Kingdom.
We apply and develop formal methods technology to systems of interest to NASA. Our current area of interest is on urban air mobility, and we are developing highly assured autonomous unmanned aircraft systems, or UAS. We apply different types of formal methods, including model checking, static analysis, runtime verification, abstract interpretation, and of course, theorem proving. Our theorem prover of choice is SRI's prototype verification system, or PVS. And as a matter of fact, we are the main developers and maintainers of the NASA PVS library. That is a large collection of developments in PVS, ranging from fundamental theories in analysis, trigonometry, real numbers, vector calculus, etc., to applications in fault tolerance and air traffic management systems.
In design, we make a clear distinction between interfaces and components. An interface describes the contract between two components, how two components should interact. During the verification of component, the interfaces and components are translated to the MCL2 language. The MCL2 tooling is from the Eindhoven University of Technology, made by the group of Professor Jan Frieso-Grote. If during model verification an error is found, the counterexample of the model checking is translated back to a nice sequence diagram and presented to the user. The user can now fix the problem and rerun verification. If no problems are found, the user can also use the design component models for generating the code, which is of production quality and can just run on the machine. Our approach is compositional. If no errors are found for each of the individual components, we know by definition that the complete system is correct.
Here at D-RisQ, we routinely use the Z notation with the proof power theorem prover and the process algebra of communicating sequential processes, CSP, with the FDR4 model checker. In addition, we use SMT solvers such as Z3 and D-Real and hide them behind widely used industry tools such as Simulink and Stateflow from the MathWorks. We've used these techniques and tools to develop and verify high integrity software, such as a flight control system and a system for monitoring and intervention for autonomous systems.
Our group consists mainly of mathematicians and computer scientists with a strong background in proof and theorem proving. And as in many other industries, it's sometimes difficult to find people with the background that is needed to apply formal methods. So one of the objectives of our research is to make formal methods available to software engineers and software developers who are working on these critical systems.
Design is made in such a way that it can be used by regular software engineers. That is, software engineers that don't have a background in formal methods. This is also what we hear back from our customers. Most teams at our customers work in an agile way, that is, an incremental way of working. If you add a user story to your interfaces and components, the model checker will tell you whether there is any interference between the newly added feature and the feature which were already there. In this way, design supports the teams of our customers in their way of working.
We anticipate that we will experience difficulties as D-RisQ grows in acquiring staff to use formal methods, but the principal direction of D-RisQ is to make formal methods widely accessible to users of approaches like Simulink and State.
Our group was created in 1988 by Ricky Butler. In these more than 30 years of continuous work in formal methods, we have many stories with great impact to NASA's mission and aviation safety. For example, we recently found issues with a system that is mandated in every commercial aircraft in the world. We found those issues and we provided a reference implementation that is formally verified and is included in the international standard that was published last month. If you are interested in our work, please visit our web pages that are available through a web search on formal methods at NASA Langley. Thank you.
Working with formal methods has always been fun and challenging at the same time. The most challenging task is how to bring all the benefits of formal methods to a regular software engineer, such that for a regular software engineer, his job is also a lot of fun and that he is not bothered by debugging anymore, but just can focus on the creative aspect of writing programs.
My experience of using formal methods is very positive in that it saves time and money. Indeed, we find it difficult to imagine not using some formal notation or approach. And my experience has shown that formal verification is becoming commoditized in some sense. And now that the challenge is the very human activity of being able to articulate requirements and express those requirements formally for verification.